Next session will start. Please come. Yeah. 你就坐在这，你坐这，没事。So, yeah, the time's up. Yeah, we're already behind the schedule. So please, let's start the next session. It's about the topic plenary session. Flow structure interaction. We have 3 presentations. So every presentation have 25 minutes. The first presentation will be given by the Zheng Chunbao. It's Dalian Maritime University. It's coming. First the speaker. Okay. So yeah, please. Professor Zheng, right? Yeah, please.
Good morning, everyone. This is my topic, drug reduction technology and mechanism analysis of bionic and water vehicle. This is the contents. The ocean accounts for 70% of the total area of the of the Earth. That contains valuable development energy and ecological environment resources. And the water vehicle plays an important role in ocean exploration. Drag reduction is the most effective means to improve its performance and save energy. Viscous resistance is dominant, which is divided into surface friction resistance and pressure drag. The surface friction resistance is the resonant force acting on the surface shear stress in the direction of motion, which is related to the viscosity competence of water under the surface area. The pressure drag is the resonant force acting on the surface pressure in the direction of motion, which is produced by the pressure difference between the front and the back, and is relative to the shape. The form of drag reduction include this force. The first one is screwed surface, the second is damp surface, and the third is hydrophobic surface, and the last is the flexible surface. For the flexible surface, the surface is flexible and deformed under the action of incoming flow. The drag reduction mechanism is improve the stability of the laminar boundary layer, slow down the change of velocity, and delay the transition of the boundary layer. In this paper, the flexible surface drag reduction technology is used to study the influence of flexible surface on the resistance of bionic and water vehicle through the co-simulation of CFD and FEM, and the drag reduction effect of flexible surface under different conditions is analyzed, and so as to provide assistance for the application of flexible surface in practice. The research contents includes first one is modeling. Using the modeling software to design the bionic and water vehicle shape. Using SolidWorks to segment the skin model. The fluid domain and the solid domain are established, and the grid congruence analysis and the timestamp independence tests are carried out. And then the pressure cloud diagram, washer stress cloud diagram, and the velocity cloud diagram are quality analyzed. And the drag reduction principle of Bionie underwater vehicle with flexible surface is discussed. Finally, the drag reduction effect of flexible surface with different thickness, materials, and the water flow lecture velocity is analyzed. The fluid control equation includes law of conservation of mass, law of conservation of momentum, law of conservation of energy. And the solid control equation includes equations of motion based on the assumption of linear elasticity, the geometry equations based on the small deformations assumption, stress and strain relationship. The collaborative simulation series includes first one, solve the flow field control equation, and then the results are brought into the stress condition and the solid control equation. Solve the solid part, and then the solved result and the deformation compatibility conditions are substituted into the flow field control equation, updating the solution of flow field control equation, and finally repeat until the result converge. This is the three-dimensional model for underwater vehicle model and the coordinate system. In the collaborative simulation, the deformation of the interface is very small, which satisfies the small deformation assumption. It can be considered that the strain is linearly related to the stress at this time, which is simplified to linear elastic material. The 10 millimeter rubber is used as the flexible surface, and the non-linear material setting and the linear material setting are used. This is the computational domain boundary condition and the physical model and the mesh subdivision. The base size is 0.1 meter. The flow field is mesh refined layer by layer, and the local mesh refinement is performed at both ends. This is the determinant for solid domain. The boundary condition is the outer surface of the flexible surface is named FSI as the interface coupled with CFD. The inner surface of structural steel adopts fixed constant. The bending constraint is set on the contract surface to prevent slippage between the inner and the outer layers. Mesh subdivision, the thickness of the flexible surface of rubber tool is 10 millimeter. The internal is structural steel material with a thickness of 10 millimeter. This is the order of the code simulation. The first one, CFD transfers the load and the load of the fluid flowing through the interaction interface to FEM. FEM transfers the displacement at the fluid solid interface of the Bionic and water vessel to CFD, which demotes the fluid domain mesh. Automatic data exchange between CFD and FEM using CSE. This is the cooperative simulation step. And then the mesh density convergence is done. And the boundary the boundary layer gets sensitivity analysis is done. And finally, the time-step independent test is done. And from the result, we can say when the time step is less than 0.001 second, the result can be considered not to change. When the time step is 0.001 seconds, when the physical time is 0.5 seconds, it tends to a stable value, but there is a slight change. When the physical time reaches 1 second, the result does not change, and the calculation convergence can be considered at this time. This is the effect of flexible surface on the drag reduction performance. From the result, we can see that for the materials rubber, for the thickness of 10 millimeter, the effect of drag reduction is effective. This is the wall shear stress field. The shear stress amplitude of the ragged surface is larger than that of the flexible surface at each section. And for the velocity fields, the afterbody has absorption effect on the fluid, which makes the afterbody appear low speed region. The low speed region of the flexible surface is larger and relatively stable than that of the ragged surface. The low speed region near the wall of the flexible surface lags behind that of the ragged surface. The region required to increase the velocity from 0 to the external flow field is thicker, and the velocity gradients can be considered to be lower. For the pressure field, from the pressure field distribution is more intuitive to say that the afterbody of the flexible surface has a better absorption effect on the fluids. The pressure of the flow field change little, and the pressure difference resistance is reduced. This is the deformation increase with thickness. From the result, we can see that the thickness of 15 millimeter has a better drag reduction rate. Deformation increase with increase of pliability. This is the result from this is the result of the effects of material on resistance. We select five materials. From the result, we can see that for the mineral rubber one, which has the the minimum the elastic modelers has the best drag reduction. This is the effect of velocity on drag reduction on flexible wall. The last is the conclusion. The first one is about the drag reduction principle of flexible surface. Through the deformation of interface, part of the pressure is released. The transition of the boundary layer is delayed. The velocity gradient and the pressure difference before and after the vehicle are reduced, and the surface friction resistance and pressure difference resistance are reduced. In a certain thickness range, as the thickness of the flexible surface increases, the drag reduction effect will be improved. When the thickness is too large, the resistance will increase and the drag reduction effect cannot be achieved. Within a certain range of elastic modelers, the smaller elastic modelers of the material, the greater deformation of the interface, the smaller of resistance, and the more obvious the drag reduction effect. The deformation amplitude of the interface affects the resistance of the model. Within a certain deformation range, the resistance will be reduced. When the deformation is too large, it will have a greater impact on the differential pressure resistance. The flexible surface has a good drag reduction effect in a certain flow rate range. As the flow rate increases, the drag reduction effect will decrease. When the flow rate exceeds a certain speed, the drag will increase. That's all. Thank you for listening.
Okay, any questions or comments from the audience? So even though I think I can have a question, and for the drag reduction, you mentioned that you are using, I think, different materials, right? So the drag reduction is mainly caused by the flexible with different materials.
Yes.
So to what extent do you can achieve this kind of drag reduction, like a 2 or 3%? Or?
Thank you for your question. We choose 5 materials for the drag reduction. The different materials have different elastic models. From our calculation, we found that for the rubber one, which has little electric modelers, have the best result for drag reduction.
Yeah. Okay. Thank you. And okay, please.
Thank you for the presentation. Regarding, you presented based on drag reduction, but regarding the application, usually the material specifications come from other requirements. What's the purpose of the research in this case? Do you aim to select materials also based in other requirements, but also in drag reduction, or is drag reduction the only limitation you have to solve?
Sorry.
The question is, okay, you have other specifications. Do you have freedom in your application to use any material? Or
no. We only choose 5 materials. five material. Only choose 5.
Okay. Oh, 5 materials.
Yes.
Okay. Okay. And are those all of those materials adequate for the application you have in mind? Because
sorry, I can't understand well.
It's okay. We can talk about it later. I'll reach you and I'll ask my question again. Thank you.
Thank you.
Thank you.
So according to the schedule, I think we can stop here. And thanks the speaker again.